This is the lesson on position and displacement in the kinematics unit. First, to define position, it's the location of an object in a coordinate system. We have a Cartesian coordinate plane here. We have our axes, our x and y axes. And any position in here extends from the origin. For instance, I have a couple of examples down at the bottom. If I have the location for 0, there's the location for 0. There's a vector that extends from the origin to that point for 0. And I could name it anything. I put a couple of examples over here. We can just call it x1. I'm fine with that. And notice that when I assign a symbol to my vector, there is a little accent over it, the vector accent over the symbol, and that's to represent that it is in vector. And we're working with vectors, so not as only is there a magnitude, but there's also the direction, and hence the need for the coordinate system. I could put a more complicated example on there. The next one I have is -5, 3. There's the point -5, 3. So there's a vector that extends from the origin to that point. I won't name it x because I reserve x names for the x-axis. This one we can let be a R1 maybe, and it has an x and a y component. You can see that has an x and a y component in here. All angles are measured from the x-axis. So when I look at the second angle for R1, this angle here, it's measured from the x-axis, and I've already calculated it. That's 121 degrees. So when you see angles, unless otherwise specified, assume that it's measuring from the positive x-axis. The graphs of position versus time have, you can notice on the axes, the independent variable t goes on the horizontal axis, that's the time, and the dependent variable goes on the horizontal, that's the position. And you can see x in meters. Okay, and as I'm looking at this, I'm noticing that whatever the object is, whatever it's doing, it started at the origin and it moved in the positive direction, these +10, +20, etc. We're going to have to translate between representations. We have multiple representations for all these concepts, and the vector representation is going to be the more powerful one as we move forward into more kinematics and onward to forces. So, it says translate the position to a vector. So if I have x of 4, that means what is the position at 4 seconds? And I can write that out. I can go over here. Here's 4. At that place, there's 2. It's 2 meters away. And I can represent that with a vector, 2 meters. Okay. 8 seconds, we can go to 8 seconds. Oh, that's a nice number there. 2, 4. It must be 4. We're at 4 meters. And this vector is twice as long as the previous one. And inherently, I defined positive to the right as positive x. All right. Always assign a coordinate system. If I drew a vector in the backwards direction, that means that the object would be in the negative zone of displacement, and that would be below the time axis here. 12 is over here. The position is 5. And so I can draw one a little bit bigger than 4. Let's see, 16, 15, 16. What is it doing? 10. I have 10, so let's draw one twice as long as that. 18. That's why I thought 18. We have a 20 meter one, so I'm going to have to draw a really long one here. And I like making the vectors represent the magnitude. So you can see the 2 is much smaller than the 20. And so we get this idea of magnitude visually, right? When I look at numbers, I don't get that. Like, I know that 4 is bigger than 5, but I know more intuitively when I look at those two vectors that there's a difference in length. This is a powerful representation tool as we move forward. Okay, x of 20, where is it at 20? Looks at 12 meters. So this would be 12 meters, and I need one a little bit longer than the 10. And those are vector representations. You may say, Sarah, it went up to 20 and then it went down to 12. So doesn't it need to have like a vector in the backwards direction, and I'm going to go back to the definition of position. Position always refers to the location away from the origin. So even though it goes out to 20 and goes back to 12, I'm still a positive distance away from the origin. It doesn't matter that I went backwards or forwards or whatever. I'm just looking at the distance away from the origin. So let's look at the displacement vector. That's what we're talking about when we move from one place to another. We're going to have a change in position, and that's what the displacement is defined as. This is a vector. If I change direction in one to the left, that's different than changing it to the right. It's a vector that points from an object's initial position to its final position. So we're at whichever way it went to move, that's the direction it points, and that's sort of intuitive. This is the formal equation for it. Notice that it is a vector equation. I have the initial position vector, the final position vector, and the change. Delta always means change. That's Greek letter delta. It's the lowercase. And by convention, it's always final minus initial. If you subtract the two numbers, you get the same number, but you'd have a sign difference, and this difference in the sign is very important here. All of these quantities are vectors, so if you have a negative or positive, you need to keep that into account, so direction matters. So when I look at A to B, it would make sense if I move from A to B, the displacement vector would look like that. And I can write it like this, A to B. There is no coordinate system assigned here. I don't know where A is relative to the origin. I don't know where B is relative to the origin. But I could say that an object moved from A to B. That was a displacement. And so as we move forward, we don't need to always know the origin. We can think about the displacement between two vectors. So I have an example on the next slide here. Displacement vector practice, and there's the equation up there, and we're going to use vectors to do this. You can see that I have a column of initial positions and a column of final positions, and I've asked us to find the final minus initial and the displacement. And so this might seem a little bit intuitive, right? If I have 2 meters, we'll define to the right to be the positive x direction. So if I have positive 2, I can draw a vector like that. If I have positive 6, I can draw a vector 3 times longer, so it's 6, right? And so what I'm going to do is I'm going to take x final, which is the 6, and I'm going to subtract off the 2, which means that if I subtract a positive 2, I'll point it in the other direction. And you can see that the remainder between these two is how far the object went. So this would be plus 6 minus 2. This would be a plus 4. So our displacement vector over here is a plus 4 meters. Okay, so that's using vectors to do that. We're going to do some more practice here just to get used to it. I have a plus 6 vector and a plus 2 vector. I just rearrange those two. And it makes sense if I start at 6 and go backwards to 2, I should get a negative 4, right? This should make sense in some way. If I have a plus 2, right, I take the final one, and then I subtract off the initial one. So I have plus 2 minus 6, and that results in what I was expecting, a minus 4, all right? When I find this final vector, I'll go from the end of the first vector to the front of the second vector. So this will be negative 4 meters like we expected it to be. Okay, here I go from negative 3 to plus 5. I'm moving a pretty long direction over the origin here, right? I have a negative 3 and then have a plus 5. Well, when I take a plus 5 and I subtract off a negative 3, that would actually be Sorry, that was a little long. The negative of a -3, right? -3 points to the left. I want the negative of that, so that ends up making it point to the right. And overall, my displacement from -3 to +5 is going to be a +8 meters. I moved +8 meters. So hopefully this is making sense to you. By this point, you're probably getting used to this. I'm going to go down and look at the last one here. -3, a -5. So it moved backwards in the negative direction. So if I take the final vector, -5, and I subtract off the -3, that means I'm going to add 3. The negative of -3 is adding 3. -5 plus 3 is a -2 meters. So this turns out to be in the negative, which we expected. It moved away from the origin in the negative direction, so its displacement is -2. So that's how to represent vectors, to do a translation from a numerical vector to a actual vector, and to subtract them. It looks a little different. We're going to keep using vector representation to help us in identifying. So I want to bring up another problem. Draw the displacement vector for each of the following intervals of time. Okay, so at t equals 0 and t equals 10, there's the 2. At t equals 0, we identified this before. It was at 0, 0. And it moved, how far did it move in the x? In 10 seconds, it moved 5 meters. Okay, so if I go x final minus x initial, that's 5 minus 0. X final minus x initial, 5 minus 0, well, that's a +5. So the displacement vector is going to be a +5 in this situation. In this case, it moved 5 meters in the positive direction. And inherently here, I'm saying to the right is the positive x. On the graph, positive x is upward, and I'm making it to the right on the page. And that's fine. I could define positive x to be upwards or to the diagonal downward. It doesn't matter. But by convention, we do positive to the right, and I'm drawing it that way. Let's go 10 to 18, right? From the time the lower bound is 10 and the upper bound is 18. So where is it at 18? At 18, it is 20 meters away from the origin. So 18, comma 20. Okay, so we go from the point 10, comma 5 to the point 18, comma 20. I can do x final minus x initial. I have x plus 20 minus a 5. And so it moved plus 15 meters. Between 10 to 18 seconds, it moved 15 meters. So I'm going to represent that with a pretty long vector, plus 15 meters. All right. From 10 to 22 seconds. Okay, so we're still at the 10 second. It wants me to go over to 22. Where is 22? Oh, over here. Here's 22. So 10 is still 10, comma 5. And we moved to 22, comma 4. All right. So between 10 and 22 seconds, we're going to note on this graph that it actually went downward, right? In between 10 and 22 seconds, it moved out to 20 and then down to 4. But between 10 and 22, x final minus x initial equals 4 minus 5, which is -1 meter. So the displacement vector in that case is -1 meter. It went backwards 1 meter. We don't care that there was other stuff going on. Okay. 0 to 30. Let's see, 0 to 30 seconds. There's 30 seconds. 30's, comma 4. So 0, comma 0. And then 30, comma 4. Well, x final minus x initial is 4 minus 0, which is plus 4 meters. And we can see that on the graph. It ends up after 30 seconds, it ends up 4 meters away from its original position. So that's how to translate a graph into the points. You can see how I used the equation and translated that into a vector. I'm using direction with vectors to indicate positive or negatives, and also the lengths of them relatively. I'm making them larger or shorter depending on the actual value, magnitude of the vector. All right, so distance is different than displacement and displacement vector. All right, I know it sounds similar, but I wanted to make this distinction, and I do it because no formal distinction is made really in textbooks that I see. So make sure you attend to detail and context when we're doing this. And here's the difference. Distance is defined to be the magnitude of the displacement. So when you're seeing magnitude, you're going to note that that's a scalar quantity, and I use an absolute value sign in order to say I want just the value. What's the value of that vector? I don't care which direction it's pointing. It's a scalar, right? So we can create the symbol of delta x just to represent that. Instead of writing all this stuff out, you can do it this way as well. Often while I'm teaching, I will write this out just to be more explicit. And again, this is a unit of length. It's just a distance, right? Which is different than distance traveled. There's the same word in there, but it's a whole different concept, and maybe more appropriately what you think distance should be. Distance is like on the last slide. I started out at 5 meters, I went up to 20, and then I went down to 4, and so I traveled a distance, a displacement, our displacement, delta x, was -1 meter. Well, if I take the absolute value of that, the absolute value of -1 is 1 meter. I traveled 1 meter. But in your head, you know that that's not how far that object actually traveled. It went from 5 to 20, which is 15. And then it came from 20 down to 4, which is 16. So overall, it's the total length of path, right, in that situation would be 21 meters. If I just looked at it before and after, I think it went 1 meter. But actually it went, the whole path traveled is 21 meters. And that's traveled between 2 points. So like if I'm looking at A to B, I can go from A to B directly, and that's what the displacement vector would look like, and I could find the length of that. You know what? I could do a whole bunch of stuff before I get to A, and that would be the distance traveled. To follow that path, that's how far I actually traveled. Okay, we're going to represent with sometimes you'll see distance in there or just a D. So that's why it's different than notation than the distance. So D is reserved for the total length of path, and the delta x is left for the formal distance concept. Okay, so watch out for this when you're doing problems. Sometimes it's not clear, but you'll get this feel like, is this a technical thing, or do they want the actual path traveled? Okay, so I have an example here. It's a 2D example, so we get to use some trig in order to practice that. On a walk, you follow a path of 3 different directions. First, you walk on the diagonal of a rectangular park. The park is 1 block east and 3 blocks north. You then turn directly north and walk 2 more blocks. Finally, you turn straight east to walk another 5 blocks. So you can see I have this grid over here. We're going to put these walks on the grid. Let's look at the directions. Draw the sketch of your path. Had that in mind. Include in your sketch a coordinate system, a vector for each portion of your path, and the resultant vector representing your final location relative to the beginning of your walk. Label each vector clearly with a meaningful symbol, not just a number. So we're going to formalize this. Okay, so let's do this. Let's make this way east and this way north. I don't think anybody's going to fight me on that. And it sounds like we're going from west to east and south to north. So I'm going to start down in this corner. It says, first you walk on the diagonal of a rectangular park. That's 1 block east and 3 blocks north. So 1 block east, 3 blocks north. So that's the first path that you walk. We can draw a vector across here, and I'm just going to call this vector A. Okay. There's 2 more, and B and C just make sense in here. You then turn directly north and walk 2 more blocks. So walk 2 more blocks north. All right, so there's the B vector directly north. And then it says finally you turn straight east to walk another 5 blocks. Walking another 5 blocks east. Whoa, perfect. 1, 2, 3, 4, 5. All right, and I'm going to call this vector C. Okay, so that's your actual path. The vector that we're looking for, it says the resultant vector representing your final location relative to the beginning of your walk. So we want the resultant vector. A resultant vector is when I add these 3 up, I'm going to get a vector that connects across the grid this way to where, so this is the resultant vector. This is the initial position. This is the final position. And this is the straight line between those 2 positions. That's the displacement vector. We're going to call this the resultant, and you can think of it as the displacement vector. Okay, label each vector clearly with a meaningful symbol, not just a number. Did that. Okay, I'm going to write some things over here I know. A. Well, when I look at A, it's 1 block east and 3 blocks north. B is 2 blocks north and C is 5 blocks east. Okay, so I'm writing down what I know. I don't know the length of R yet, nor do I know the angle of it, right? Because there is a angle relative to the positive x-axis here that we would need to have for direction. And looking at B, it says, what is your final location relative to where you began your walk? Give your answer as a magnitude and a direction relative to east. So we're going to need to find this angle. Okay, so we know how to add vectors. When I look at this vector here, the resultant vector, I can note that it has 2 components. It has an x component, which I am going to call Rx, and it has a y component, which I am going to call Ry. No surprise there, right? Okay, so if I wanted to find the magnitude of R, I could take Rx and square it and add it on to Ry squared. Pythagorean theorem says that that relationship has to be true. I could also find theta when I have the value for Ry and Rx. So that's sort of the larger plan. I'm going to shoot for calculating Rx and Ry from the A, B, and C. Once I get those, I can find the magnitude of the resultant and the angle that it's oriented at. So when I look at Rx, it will be the x component of A and the x component of B and the x component of C. I can dissect these 2 dimensions and add up all the x components of the 3 vectors and add up all the y components of the 3 vectors, AY plus BY plus CY. You could do this with a chart. That would be appropriate as well if I have x and y here, x, y, and I have my 3 different vectors, A, B, C, and the resultant one. Each has a component in theory in the x direction, each has a component in the y direction, and when I add all of those up, I get the resultant in Rx and Ry here. Okay, so this is a chart version and this is just an equation version. I encourage you to use which one you prefer. So I'm going to go ahead and plug in some values here. A has 1 east and 3 north, and I can put positives there, but they're all positives. So I can say AX is 1. All right, you see what I'm doing here? B is 2 north. It has 0 in the x direction, and it has 2 north. C has 0 in the y direction and 5 east. So then when I go to add these down here, I can add these up down here, equals 1 plus 0 plus 5, which is 6. AY plus BY plus CY, well, I get 3 plus 2 plus 0, which is 5. And so RX equals 6 and RY equals 5. Those were the two values I was going for. So we know Rx and Ry, and we can take those and use them in the equation that we set up before. So we have 6 squared plus 5 squared, and you run that through your calculator and you get 7.81, and our units here is blocks. So that's how far from the initial location to the final location you traveled. Let's figure out the angle. Let's use a trig function, opposite over adjacent. I know Ry and I know Rx, so the inverse tangent of Ry over Rx has to equal theta, so I can put that in. Tan inverse 1, Ry is 5, and that's 6, so we expect an angle less than 45. If it was the same thing, top and bottom, tan of 45 is 1, so we use something less than 1, so it'll be an angle less than 45, and when you calculate that in your calculator, it is indeed 39.8 degrees, and that's that angle there. Notice that I use the symbols consistently, so if someone was looking at my work, they can see theta there and theta down here, so they know that that angle matches up. Okay, so I have a magnitude and a direction. Great. 7.81 blocks, 39.8 degrees. So we answered that question. I can put relative to east here. Another way we could say that is north of east. We took from east, we extended upward north, so it's north of east. There's another part of this question that I wanted to get to. What is the distance you traveled? How is this different than the displacement? So in the previous problem, we found the displacement vector, right? 7.81 meters at 39.8 degrees north of east, all right? That's what this is, okay? How is this so let's calculate the distance. So the distance is traveled along these lines, right? A plus B plus C. So we want the distance is going to be whatever A is plus whatever B is plus whatever C is. We don't care about direction, we just care about value. How far did you actually walk? It wasn't the 7.81, it was farther than that, right? So A, we can find the value of A. We know A has to be the square root of 1 squared plus 3 squared, right? If I use Pythagorean theorem on that one, I have 1 on this side and 3 on this side, and so the hypotenuse has to be the square root of 1 squared plus 3 squared. So then we can add on B, which is another 2, and add on C, which is another 5. You get the distance traveled to be 10.2 blocks when you run this through your calculator. And that's bigger than the 7.81, which we expected. Oh, that should be blocks. Okay, how is this different? So you're seeing how it's different. There's the actual path traveled, and then there's this displacement between.